Hello and welcome back. Let's review examples 2, 3, and 4. In example 2, we saw that the x values for which the series converged was just a single x value of 0. It happened to coincide with the center of that power series. In example 3, we saw that the series converged on an interval, so on this interval from 2 to 4, where the center of the power series was right in the center of that interval of convergence. Now, in this case, we had to check the endpoints to see if the series converged at the beginning endpoint and the ending endpoint. do endpoints begin? I don't know. But the left endpoint and the right endpoint. Then for example 4, we saw that this power series converged for all values of x, for all real numbers for x. Now it turns out that there's a theorem that says those are the only three possibilities we could have for a power series converging. So given a power series with center A, it's either going to converge only at its center, only at x equals its center, or it'll converge absolutely for all values of x. And we had just said in example 4 that it converged absolutely, it converged for all values of x, but because we used the ratio test with the absolute value bars, it's converging absolutely in those cases as well. Or the third condition would be, or the third possibility would be that the power series converges absolutely on an interval, some interval of convergence. So here we're writing the interval as x minus a is less than r in absolute value bars, x minus a in absolute value is less than r, and diverges for x minus a in absolute value greater than r for some r, some positive number r. Now here you need to check convergence at the endpoints. So when x minus a in absolute value is equal to r, and that's exactly what we did in example 3. R here is called the radius of convergence. So for case 1, we would say that r is equal to 0 because we only get convergence at a single x value, so the interval is kind of like 0 width. And then for case 2, where this power series converges for all x, for all real numbers, we would say that the radius is infinity. One way you can visualize the case 3 is if a is right in the center, then your endpoints will be a minus r and a plus r. That would be your interval of convergence right there. From a minus r to a plus r. Now, you again have to check to see, does the power series converge at a plus r and a minus r, and that's checking the endpoints, but at least it'll converge in between. Let's look at example 5 and find the radius and interval of convergence of this power series. So the interval of convergence, again, means what values of x does this power series converge? And the radius is going to mean what's the radius of that interval of convergence. That's just going to be halfway across the interval of convergence. And in the case of case 1 and case 2, the radius of convergence might be 0 or infinity. Let's check to see what we have. So here we have the series n going from 0 to infinity of negative 3 to the n times x to the n over the square root of n plus 1. We're going to start by using the ratio test again. You can see the ratio test is very important. We'll take the limit as n approaches infinity of a sub n plus 1 divided by a sub n, or multiplied by the reciprocal, so that's going to be square root of n plus 1 over negative 3 to the n, x to the n. All right. Now there's some cancellation that happens. N of the negative 3's will cancel. You'll have one of them left on the top. N of the x's cancel, and you'll have one of them left on the top. Now we can write the rest of it. We can write the the square root of n plus 1 over the square root of n plus 2. We're going to go ahead and write that in a single expression as the square root of n plus 1 over n plus 2. That'll help us evaluate the limit a little bit better in the next step. Now we have a negative 3 times x as well. And now what we have here is the limit as n approaches infinity of, well, the square root is a positive square root, so that doesn't get affected by the absolute value bars. Now the absolute value bars are going to make that negative 3 into a positive 3. So we could write a positive 3. I'm going to write that positive 3 out in the front here. And then the x is stuck inside the absolute value bars because we don't know if x is positive or negative at this point. Now the limit as n approaches infinity of n plus 1 over n plus 2 is going to be 1. And the square root of 1 is 1. So overall, we're going to get 3 times the absolute value of x. Oh, and again, remember that this is our L value. So as long as that L value is less than 1, we've got convergence. Absolute convergence, in fact. So if that L value, that 3 absolute value of x, if that is less than 1, then by the ratio test, we have convergence. Now we can solve this for x, and we'll get that if x in absolute value is less than 1/3, we've got convergence. I'm highlighting the 1/3 because you'll see how that relates to the radius of convergence. What I'll do is I'll first write the interval of convergence, or the basic interval of convergence that we have so far. So the absolute value of x less than 1/3 means x is between negative 1/3 and positive 1/3. So there you can imagine your interval of convergence, where x equals 0, which is the center of our power series, is right in the middle. And so you can see the radius of convergence in that picture. It's the distance from the center out to the sides. The radius is like half the diameter of this interval, the diameter being all the way across the interval and the radius being halfway across the interval, which is going to be from the center out to either of the endpoints. But if it's written in this form, you could have this picture in your head, but you can imagine that if you have it in this form, this is your r value right here. So if you have it in the form x minus a in absolute value is less than r, the radius of convergence is that r value right there. That's because of your picture. Because you can have that picture in your head. You don't have to write it down, but you can have that picture in your head. Most of the time for these, we'll just write r equals 1/3, but I'm writing it out here since we're just learning about the radius of convergence. Now, we still have to test the endpoints, x equals 1/3 and x equals negative 1/3. We don't know if the series converges or diverges at those endpoints. So let's test them. The way we test is we plug in negative 1/3 into the original series. What are we plugging it into? Well, we're plugging it into the x, right? When you plug in x equals negative 1/3, we replace x with negative 1/3. in the original series. And when you think about -3 to the n times -1/3 to the n, you get these pairs of -3 times -1/3. You have n of these pairs, and each of the pairs will multiply together to give you just +1. So at the top, you just get +1 over the square root of n plus 1. Now that series, we could say, diverges. It diverges by the integral test, or possibly by a comparison of some sort to 1 over the square root of n. Let's just write diverges by the integral test. Let's write or by comparison to here we have to be slightly careful. N equals 1 to infinity of the square root of n. We can't start off at n equals 0 because then that would make the bottom 0 and that would be undefined. So we'd have to compare it to the series 1 over n, square root of n, but n going from 1 to infinity. Just a subtlety, but ultimately it doesn't matter what n you start off at as long as it doesn't make the terms undefined. But the comparison is still going to work there. So at -1/3 we get divergence. Let's see if we get convergence at x equals 1/3. Now here we have a -3 times a 1/3. We have all those n pairs together, but each of those pairs, when you multiply the -3 times the 1/3, will give you -1. So you have n of these -1s that result, and so you get -1 to the n on the top. Now this is an alternating series, so we can say this one converges by the alternating series test. If you look at the b sub n's in this case would be 1 over the square root of n plus 1, and those b sub n's would be positive, they'd be non-increasing, and they would go to 0 as n approaches infinity, so convergent by the alternating series test. So putting this together, we have our interval of convergence. Is between -1/3 and 1/3, but including 1/3 and not including -1/3. We have convergence at x equals 1/3 based on our work right here, and we do not have convergence at x equals -1/3 based on our work up above. So there's the interval of convergence. If you actually just found the interval of convergence and then at the end wrote the radius of convergence is 1/3 because that's halfway across the interval of convergence, that's also fine. It's kind of nice to notice it ahead of time, but a lot of times when I'm doing these problems, I'll just find the interval of convergence and then look halfway across, and that'll be the radius of convergence. So to summarize, how to test power series for convergence: you can use the ratio test like we've done for all of these problems, or the root test to find the radius of convergence. Then if r is equal to 0, this is taking like a kind of a backwards approach of finding the radius of convergence first. If r is equal to 0, the interval of convergence will be x equals the center, and then the series is going to diverge for all the other x values, x not equal to the center. If r is equal to positive infinity, the interval of convergence will be all real numbers, -infinity to infinity, and the series will never diverge. Otherwise, you know that the series converges absolutely on the interval from a plus r to a minus r to a plus r, so that's x minus a in absolute value is less than r, and it'll diverge for when x minus a in absolute value is greater than r. But then we have to test for convergence at the endpoints, like we did in a couple of the examples in this section. So usually we would use something like the comparison test or the integral test or alternating series test to check the convergence at the endpoints. All right, so that concludes this section. Thanks so much for watching, and see you in the next one.